maybe start. Right, so what we were at on Monday, we were deciding that we should figure out, what types of germs definable in H, in R and X have good holomorphic continuation to the complex plane. So we gave a description of all the definable one variable germs. We constructed the Hardy field inductively by double induction. That gives us some information, some inductive structure to study these terms. Okay. But now, we should think about a little bit. That's what I want to do today. What do these holomorphic extensions look like? And since you're talking about terms, right, and everything is given by composition of terms what do you call it? The basic relations of the language, ln exponent log. That's where we should start. So things that we can easily extend. Okay, so I guess easy example, scalar multiplication is by so I'm going to write as MR, right? MR X times X, where R is a positive number. That's pretty obvious, right? That just extends to the whole complex plane. Right? I think that we have much to worry about, but we will have to at some point. We can look at power functions, which aren't exactly in the language, right? But still, I'm still interested in those. PR of X, which is X to the power R. Again, R is real number. Okay. So of course, if R is a natural number, then again we just extend period, right? And what about for X to the R, right? The typical extension is everywhere except on the negative real axis, right? So you can extend like the domain of the principal branch of the logarithm. That's what you can use to extend the complex plane. Okay, so those extensions I'm going to call PR bar. So C minus step. Okay, so they do extend this way using the principal branch of the logarithm. But there's a problem, right? It becomes multi-branched when you cross that line. So for natural numbers, it's not a problem, but there's still also a problem in that case because the holomorphic extension becomes no, it's not a problem. Let's see, and of course the logarithm itself, same thing, right? So maybe I should have said the logarithm first. Logarithm steps to say the principal branch. Okay. And whereas, let's see, exponentiation, that's just entire. Right. Now, I don't like these extensions all that much because, well, either I have branching happening, or in this case, of course, we have a periodic, the period function, right, in the imaginary parts. And why do I not like that very much? Because again, those are just the basic ingredients for my terms. Now I have to compose. So in order to describe compositions, the right extensions of compositions, I also need to understand their images somewhat. Right? So to see where I end up. So, and especially this one here, right? I don't like because of its periodicity. So another way to study extensions, holomorphic extensions, where this will not happen, as so, right, is to study holomorphic extensions to the Riemann surface of the logarithm. All right, so let's just define this Riemann surface of the logarithm. It's a very standard construction. As a set, it's just the interval 0 to infinity cross R. Okay, so the closed right half plane, so to speak. So we have two coordinates, and those are, you think of those two coordinates as, sorry, no, that's it. Okay. You think of these two coordinates as polar coordinates, points in the plane, complex plane. Okay, so for a point, and usually I use the letter X for points in L because that's closer to the real line than the complex plane, where I use these. Okay, so for X in L, right, it's the radial coordinate and the angular coordinate, so to speak, right? So we're going to use modulus of X to denote R, right? And the argument of X. The N. Sense? Right. I hope there's not any big surprises here. Right, and why is it called Riemann surface of the logarithm? It covers pi covers via map pi complex plane. How do we define this? Pi of r comma theta is just r times e to the pi. That's the common map. Okay. All right, so I think that's all pretty familiar. So what I now mean, right, instead of looking at these holomorphic continuations on that complex plane, what I want to look at is instead holomorphic continuations on L with values in L. Okay, and you'll see why I like that better when we look back at these examples. Again. So scalar multiplication, right? That has. So we think in L. I think of the angle 0 as representing the positive real halfway. Okay, so our positive halfway sits in there. That's why I use the letter X for the things in L. Okay, scalar multiplication. What does that correspond to? Again, I'm going to write bar here. So, what does it extend? Well, you multiply the modulus. Sorry, what am I doing? Oh yes, no, I'm mixing up r's.
So you could write r x absolute value x.
Yes, I could write that. Value x and the theta stays the same. Right, so it just moves. It gets multiplied. The x coordinates get in the L plane gets multiplied, and the y coordinate does not. So that's an extension. Okay. What do I mean by holomorphic here? I claim that's holomorphic. Why is that holomorphic? The problem with the Riemann surface of logarithm is, well, maybe let me do the second example before I explain that. Right? Powers, it's also easy, right? It just means raise the modulus to power r and multiply the argument by r. Okay. So again.
You're not sure making a change of coordinates, but your first coordinate is just that x, not also x fine. Or your six. But the domain is
No, x here is an element of L. Right, so here I'm writing, so I identify the positive real x's with the elements r comma 0. Okay, and then now here we just have the elements r comma theta. Okay, so it's from L to L. But as such, a very easy function to define. The problem with the Riemann surface is that, yeah, we can easily lift multiplication to the Riemann surface, okay, as an operation, but there's no addition. So on the Riemann surface, we can lift other functions like here, but there's no addition, no global addition on L. Which means, right, what do I mean by holomorphic if I can't define the derivatives? If I can't define the difference quotient of two functions? So what you have to do is, you have to consider L as a holomorphic manifold.
So L, this map pi is a covering map, so the analytic structure on C minus L0 lifts to L.
Yes, that's a complicated one. That's not the one I will be working with because it's not injective. So, right. So, in order to more easily describe the holomorphic structure of L, right? So, manifold. And it does have a single chart in the right set with a unique chart. Log. So this is a bijection. So the chart is parameterized by complex plane. It's very simple. Log of r comma theta is what is it?
Log R plus
log r. There you go. Okay.
but this must be the same one as
It's the same holomorphic structure, of course. Yes. Yeah. But you don't want to compute with pi because pi is not injected. So you want to use this in general when you try to compute things. Right. So that really just means that if I'm trying to decide what is the derivative of a match from L to L, I have to pull back via log to C, compute its derivative, and then push it back. That's what this means. But here we can do it without having to worry about non-injectivity. Okay, so I use this thing. Let's see, that means right, so just so as not to confuse things too much with what we've done so far. But what we have done so far, we were looking on the complex plane, right? We were looking at terms at plus infinity, right? On say standard quadratic domains in the logarithm, what I call the logarithmic chart. But there was still a logarithmic chart of the complex plane, right? That was to take 0 to infinity. So we were looking at things like standard quadratic domain in the complex plane. Now, how does that lift up, right, to L? So up here, I'm going to try and draw L if I can reach it. Right, it's only really a half plane. Okay. Well, the right half plane of C lifts up to a strip on it, right? Where you have minus pi 2 pi root 2. Okay. And so the standard quadratic domain that I was drawing here, this guy, will map in, pulls back into something like that. Okay, on it. And now, if we go back to the complex plane via this chart, it looks different again, right? This and the complex plane is really just like a shift to the left, where 0 becomes minus infinity. That's really all it is. Look at it. Okay. So this is back in the complex numbers now. The strip is still the strip where the imaginary part is pi over 2 minus pi over 2. Two lines. And now, let's say if the point 1, 0 is here, this is for reference. Right, then that will correspond to the point 0, 0 here on the plane. And that will form a standard quadratic domain in this chart will still look like this. Something like that. Makes sense? And so, right, so we have this map here, this is pi. And what connects those two, right? The missing one here is just the exponential function. Okay. So when you look at it this way, right? L, as I defined it, is actually a perfectly nice definable structure in our RNA. That's a nice final set. The only things in this entire picture that are not definable in our X, that's this guy. So. And the full complex X for the same reason. They both have this infinite oscillation. Replicate human structure. Anyway, so if I want to decide whether or not these are actually holomorphic extensions, I need to work in this chart. Hold it back to this chart. Check it is a holomorphic function, and then you win. Right? For example, if I pull this one back via the holomorphic chart on the left there, what do I get on the complex plane? I just get translation by the number log R. Okay. If you pull this one back, you get multiplication by R in this chart here. Of course, those are holomorphic, so everything is good. Okay, so these are holomorphic extensions for those two basic functions. Log now, right? How does log extend to the Riemann surface? Well, down here, we have the principal branch of the logarithm. Okay, in this chart. And you can use that to define the function extension of log up there. Okay, so let me see what that looks like. So log extends to, well, let's call this log bar. So it doesn't extend to the full Riemann surface, right? Again, in this chart, we have to omit the negative real axis, which means we have to up here omit this. Okay, for the whole extension. So log extends to almost of the entire L except 0, 1 times 0. Then it will take values in L. See what's the right way to do this? You just look at these charts, right? Right. So to make this definition precise, right, if I restrict pi to the strip between what the argument is between negative pi and pi, it's injected. There's an inverse. Okay, so let me call that pi 0. That's the restriction of pi to the set where the argument makes is less than pi. That's injected. Right? That maps that strip to the complex plane minus the negative real axis. Right? That's actually exactly strip of opening pi. Right. So I use that guy to define my log over here. Right. That's just going to be log bar of x. Let's see what we write here. I'm going to write first send x down to the complex plane here, right? So that will be everywhere except the negative real axis, can be landing anywhere there. And then just take oh yeah, right, yeah, that's fine. And just take that back up via pi 0 inverse. Because I do want to have the log. Okay. So in a way, right, by doing this, I already computed the log of x. So I don't want to go over here first and then back up. I want to actually use pi 0 inverse directly. And we'll compute the log. Okay. Okay. Let's see. Right here. So let me write. Right. So this kind of set, these strips. Right? These are sectors on the Riemann surface. So this kind of set is going to be set of all points. The argument absolute value is okay. So those are the kinds of strips. Sectors or sectors like this chart here, they look like sectors. So that's what they usually call. Okay, so the logarithm, right? It extends to almost the entire Riemann surface of the logarithm, except that red line, half line there, the segment. Takes values in the Riemann surface of the logarithm, but these values are all in the preimage of pi 0, so they're all going to be contained in the strip opening pi 2. No, pi. So.
Do we not get copies of that red line missing every 2 pi as we go up?
What do you mean?
So let's say, for instance, that we
Missing
have
from what? Missing from what?
from the domain of log bar. Let's say we have our x as like the r is 1/2 and the
No. See, again, look at this chart. All I have to remove is this portion here, right? In this chart, after
I see.
which only removes that segment. Everywhere else, the log extends to. Yeah, this is all I'm doing because once I've removed this, that just corresponds to removing this particular segment. Huh? repetition. We're not using pi. We're using this other chart.
Right.
And then, yeah, and then other than that, it's defined, but the image is contained in the strip of open pi. So all of it. The logarithm collapses the entire Riemann surface to the strip.
Right.
Yeah. Okay, but it is injective, for example. This is an injective map. Log is injective, and pi zero inverse is injective, so it's injective. So, repetition. Okay, now from that, of course, we get the extension of x plus the inverse of this thing. So x extends to r. So this will now be defined on the strip, which is the image of the log. And we'll cover almost the entire Riemann surface except for the red center. That's the inverse of log r. Make sense? So these are all biholomorphic maps, in fact, in these domains. Yeah, so right there covers a lot of maps. Well, like I said, we want to figure out holomorphic extensions of all terms, all maps defined by terms, which means I have to be able to compose. Have we covered all the functions in the language by this?
And also add, of course.
Yeah, well, exactly, right? We haven't covered addition. What about x plus x squared even? Right? Addition does not extend on the Riemann surface. It doesn't make sense. It's an operation. So I can't, right? Even though I can do powers, I can do x log, I can do multiplication and so on. I cannot do addition. So what do I do about polynomials? What about convergent power series? Well, luckily, complex analysis or complex analysts have done this stuff for a long time. So this is just a matter of complex analysis. And again, this is the right chart to think about here. So let me state what happens in general here. So consider a set U in the complex plane. I'm thinking at the moment as U is being in this chart. Okay. Assume 0 is not in this domain. And consider a function f of U, which is also never 0. But holomorphic. So under what condition, right, it's a very general thing. Under what condition does a map like this have a logarithm on U?
Simply connected.
Exactly, yes. So if U is simply connected, then there's a holomorphic. G on the same U such that log compose, no, sorry, no, it's not what to say.
That is e to the g.
Yes, right. F is equal to X composed with G. Okay. So yeah, how do you prove this? Well, if F is X per G, right, its derivative is F prime over F. So what you and F prime over F, by this assumption here, is holomorphic, but because it doesn't have any poles on U. So you just use an path integral, fix a point and turn any point in U by an arbitrary path to your point and take the integral of F prime over F. Use that to define a holomorphic function on G, on U. And that's exact whose exponential is going to be F. That's how you prove it. The very classical result, Z rooting. Williams book has this exactly the same. Okay. So how do I use this here? Well, I guess. Opposition or corollary or something. So it's a similar setup, right? Except with what we have in mind, right? So again, assume U doesn't contain 0. Domain, then U is never 0 and holomorphic. Same setup for first, right? For now, we're trying to see under what condition we get a holomorphic extension from L to L and where. Okay. So here, what we're going to assume is not that U itself is simply connected, but that it's lifting to the Riemann surface. Simply connected. Okay. So if the lifting is simply connected, then I get what we want. Then F lifts to a holomorphic map or a function, which I'm going to call F bar, just like in the examples. So this F bar is going to be defined everywhere on pi inverse of U and takes values in L. It has to follow the property F with pi is the same as pi. Okay, so that's exactly the kind of thing I want. Extension on the Riemann surface. Okay. And yeah, it follows directly from that existence of branches of logarithm of functions. Theorem of Hilbert. So what? Let's see what's the. So what do we know, right? So I'm going to look at the set E, which is I'm going to take pi inverse of U, which I know is simply connected by assumption, and then take its image in the logarithmic chart of the Riemann surface. So now I have a simply connected subset of the complex plane here. Okay. So on this simply connected set of the complex plane, well, right. So now if I look at X of V, I get U back, correct? For what? With the last map there from the log chart of L back to the complex plane, I get U back. Okay. So that means F composed of X is a map on V that's never zero and it's holomorphic. And since V is simply connected, I can apply this, right? So there is a logarithm where there's a G and V such that F composed with X is equal to X with G. Okay, now I just have to pull this G back. That's the function I want. And so take F bar to be big X is the inverse of this map, this chart, right? So X composed with G composed with no. Yeah, the conjugate of G. We had a chart. Is my function F bar. Now you can. Okay. And so with that, we can take care of all the convergent power series and the polynomials and things like that. More examples, maybe. And right, what's important is again, in general, like if you have let's start with polynomials, right? So just to explain a little bit, yeah. Take a polynomial. It can even be the complex coefficients for this particular thing. I mean, you're not going to do that later, but it can be. Polynomial nicks in 1 over x. So large or small doesn't really matter, right? To take something like this, it has an obvious extension to a holomorphic map on the Riemann surface, but it will be periodic, right? And it will be C-value, not L. So what this theorem or this proposition here does, it unravels the periodicity of the function, it makes it injective, right? Making it, extending it into a function from L to L. Okay, so that's right. So this applies here because let's see, choose some positive A such that all zeros F are inside the disk E A, right? So they do that, it's only finitely many zeros. So they're inside the disk, which means the complement of that disk, right, is a set where this function here is never zero. The holomorphic function defined by this is not zero. In my proposition there, I will take U to be the complement of this. Okay, so set dA, which is the set of all Z, such that absolute value modulus of Z greater than A, right? So it's an annulus in the complex plane. Its pre-image in the Riemann surface of the logarithm is just the right half plane, so it's simply connected. And so I can apply it to that. Pi inverse of U is equal to the half plane in L, find to be set of all X in L, whose modulus is greater than A. Right, this is simply connected. And F is never zero, right? So F is never zero on the original D of U, D of A. Oh, yes. And so we can apply the proposition. And that unravels it, right? So the thing is, if you take so this F bar here will go from H L A to L, right? If you compose it on the left with pi again, then you find the other holomorphic extension. The complex value is going back, right? The one that carry on. Does that make sense?
Extension does depend on what A you chose.
On what?
A you choose.
Yes, it does. Right. So as long as A is big enough so that F has no roots in D of A, I'm fine.
Don't need to have this show up in your notation.
Well, it does. U is D of A. So this
No, an F bar.
Sorry?
F bar. Saying,
No,
I'm
no,
defining an extension.
Yes,
You're
sure.
never gonna have to worry about this.
No, because I'm going to be interested in the terms. And it's
Ah,
infinity. So,
all right.
no, yes, of course, it depends on A,
Just checking.
but it's coherent, right? If you use different A's that work, then whichever defines the smaller domain on this, they agree on that domain. So that's depend. As defined here, it does depend on A. Okay, so we can lift polynomials near infinity, since that's what we're interested in, but we're interested in germs of plus infinity. But we also have to be interested in germs at 0, and it's really no different there. It's very similar. Right. So for convergent power series, in one variable, right? Again, right? If it's not identically 0, then it will have only finitely many zeros. So in some sufficiently small disk around 0, there are no other zeros than possibly 0. Right? And 0 doesn't interest me because that's not part of the Riemann surface. So if it's convergent, and A is positive such that if C is not 0 for all Z, the deleted disk B 0 A. Okay. Then the same reason applies, right? The pre-image of this annulus or deleted disk is again a simply connected subset. In this case, the left-right plane, a left half plane, the Riemann surface, so it's simply connected. So I can lift F up there. And F lifts F bar on the pre-image of this deleted disk, which is I'm just going to write it. Okay. And so here we have two possibilities for functions like this, right? In fact, yeah, there is. So it lifts, right? This proposition doesn't really say that it's a unique lift. Right? So here we can see there are some cases where we make the choice. But most of the time it's canonical for what I use, but there's one where it's not entirely canonical. That has a bit to do with your remark earlier. Here it matters. So what do I mean? So if it's possible that the series f of 0 is equal to 0. So then what happens? Lifting has the property that f of x in absolute value goes to 0 as x modulus of x approaches 0 now. Okay, so that's one possibility. So it really defines a function that's close to 0 in some sense. But what if f of 0 is not 0? Well, then it could be positive, right? And in that case, I would like the extension, right, to map 0 to b as well in the Riemann surface of the logarithm. But what's b in the Riemann surface of the logarithm? We said the positive real half-line corresponds to argument equal to 0. Okay, so that chooses a point for the image of b. So then we choose we choose f bar such that the limit as x modulus of x approaches 0 of f bar of x is equal to the point b0. It could be any of those points, or it could be the point b comma 2 pi instead, right? So I could also say that I want it to be there instead of b0. But if once I've chosen this point that is not really in the image, right? All the other points, all the other image points will be close to that point on the Riemann surface. Okay. So of course, yeah, what do I mean by this limit, right? The topology on the Riemann surface, take the box topology. That's fair enough. Okay, and so, right, so this is a canonical choice because we have said, yeah, we interpret the real numbers as being the numbers on L with 0 argument. For negative real numbers, right, there's at least 2 equally canonical choices. If it's b less than 0, well, then it's either going to go on the line where the argument is pi or on the line where the argument is minus pi, or any one of the multiples of that. So I don't know, then I don't want to make the choice. Then choose either the limit of f bar to b minus b comma pi, or minus b comma minus pi. Any one of those is equal to canonical as far as I know. It won't really matter. The point is the functions, right? The image will concentrate around one point. It's not going to stray far. That happens in these cases. But when it's 0, it does not concentrate on the Riemann surface.
You wrote minus b there, but b
Yeah,
is already negative.
B is exactly, B is negative, so minus B is a positive coordinate, which is the only thing allowed on the Riemann surface.
Okay.
But so the negative is represented by pi or minus pi as an argument.
Right.
But again, this has to do with the fact
Yeah.
that negative doesn't make sense on the Riemann surface.
Right.
Plus minus does not make sense on the Riemann surface. The only way to represent something like this on the original chart is by playing around with the argument, choosing an argument.
There's no particular reason why you don't just pick one every time? Pi?
But I don't, yeah, at the moment I don't need to.
Right.
When I need to, I will. Okay. All right. So, and so that also, right? And all these holomorphic extensions I have defined here so far, you can actually check that if the original domain U was definable, then the domain to which we extend it to is also definable in Rnx. Okay. That's just a single check with all the charts and everything, right? It's all defined. The only thing that's not defined was pi index. But these liftings, right? If U was a definable domain in C, then pi inverse of U is also definable in L. But here is an example where this is not going to work. Once again, this is with addition. So let me finish with that. So A greater than 0, look at the translation. GA of Z in the original plane, right? It's a nice function. Okay, so not even saying addition, just addition by a fixed number. Translation. So then, as long as this is not 0 on a domain, I can lift it. So for let's see, yeah, I guess the restriction to D of A, right, interplane, so that the annulus satisfies the assumption. Proposition. So we have a lifting. A restricted to D of A lifts. Because again, D of A, the pre-image is simply connected. Lifts to what I'm going to call T of A bar on the half plane to the right of A, right, into L. But what does this image look like for this guy? The rate is still definable, right? But the map is not definable because it oscillates. There's my given surface. Here is A. Right, so the right half plane, that's the domain of my translation map. The image of this domain will have boundary that oscillates like a side function. Infinite many times. It will be everything here. Because here, right, translation goes to the right, but then at level pi, at argument pi, the translation actually goes to the other side. Yeah, I'm not sure I did draw this right. Is that correct? The angle 0. No, it's exactly the other way around. That's when you get the farthest. So or this again. So this, and when we have pi, right, so we are minus a. So then we are the other end. There we go. Okay, so the image is not defined in any order structure.
Could you give an explicit formula for this TA bar?
No.
In terms of
No, it's the same. It's going from the proposition. So here, do that. So you have to take, right? You have to get its logarithm according to rooting. That's G in the log charge of L, then lift it back up, conjugate it. Here we go. But it does this, right? I mean, all it does, right? When the argument is 0, right, it moves everything to the right by a. So yeah, just think about it a little bit. But that's all it does, right? So this oscillates infinitely often. It's boundary, so it's not a defined. The image is not defined, for example. Not that I necessarily care about that, but just to say, this introduces oscillation. Translations. Of course, you can think, right, translation must be important since we're talking about plugging things in. So this does play a role in how we describe things in general.
Is there a reason why we want to take out an entire disk and why we can't get away with, say, just taking out the closed line segment between A and 0?
Oh, in fact, you can extend it, I believe, to everything except A itself. It still works. Because everything except A itself still lifts up to a simply connected set, doesn't it? No, no, it does not.
Well, you can't include 0.
No, that's right. No, you're right. Don't take out the segment between minus infinity and 0 and 8. Sorry. Yeah. Something like that. Yeah, that's correct. But that is not so important for us because we are going to study what happens at the
Okay, if we're only
So-
studying
so-
ending, yeah.
Just the same for the log, right? I mean, the log, like I said, it collapses everything. I'm only interested in the end in what that does near infinity, not zero. Okay. Okay, so now we got all the pictures you can think of a little bit. With all this information in mind, right? The only kind of question now is just we know how to describe the terms by induction, by construct them inductively, right? We know holomorphic extensions for pretty much all of them except addition. That's where it becomes a little tricky. We have to use the convergent power series instead, things like that. Okay. Using that now, right? Find the right statement that describes the holomorphic extension property of any term, so that you can then prove it by induction on terms. That's the only thing. Right? So we'll do that on Monday.
Monday. Oh, yeah. You're right.
Monday, yes. Yeah, I'm not here Friday. So.